So this is module 1, lecture 1 of the engineering statistics and linear algebra 18 EC44, which is single random variables. So you can call it as a random variable or a single random variable. Really speaking, I should not have written variables here, either random variable or single random variable. So a random variable is just a function that assigns a real number. So this is very much important, real number, called an observation to each outcome in S. It is denoted as xa is equal to x suffix a. So a might be a what you call a particular case of a random variable. The domain of the random variable x is all outcomes such as a. So a becomes the outcome. S is the what you call space, sample space, and its range is all observations such as xa that are in Sx, right? So outcomes are a in the sample space S, and its range is all the observations whatever we have, which takes the value xa that are in Sx. Now this Sx and the S we should be able to differentiate. So for that we have written here a sample space S contains all possible outcomes from random experiment. And the sample space Sx is the collection of all real numbers that result from the outcome of S. So one point in random variables we should remember is not all the outcomes are equally likely. Not all of them are equally likely. Some of them might not be possible at all. For example, you can say you have a dice, right? So the dice might be 1, 2, 3, 4, 5, 6. You have in the dice the values 1, 2, 3, 4, 5, 6. That will become the sample space, yes. But the dice is so much crooked that 6 never occurs. Then Sx will contain only 1 to 5. So that's the difference. So whereas A can take 1 to 6 values, Xa can take only 1 to 5 because it is highly crooked and 6 never occurs. Okay, so that's the difference between S and Xs. Sometimes we don't differentiate between S and Xs, but sometimes when we say that that there is, out of all the possible outcomes, not all of them might be present in the what you call possible in the so to say observations, right, or outputs. So by convention, random variables are denoted by the uppercase letters near the end of the alphabet. For example, capital X we have considered here. Similarly, U, V, till Z, although we can have exceptions for this convention. Now this is how it looks like. This is the sample space, yes, whereas this is the real values Sx. So from ABC, which belongs to the S here, you can have XA, XB, XC and all that which belongs to Sx. So from A we have a mapping to XA. From C we have a mapping to XC might be, or XB. From B and C both you can have mapping to XB. So it can be 1 to 1 or it can be many to 1, but it cannot be 1 to many. The point is it cannot be 1 to many. Okay, let us see some of the examples of the applications of the random variables. So first is the noise which occurs in the communication, what you call link, are the elements of S. The measured average power of each noise signal is a real number and is an observation in Sx. So power might be considered as an observation in Sx, whereas noise itself, different types of noise which occur in the communication link might be the elements of S. So a particular value of the noise at a certain instant of time will become the observation which is in Sx. Similarly, you can have manufactured products in use serving customers or elements of S. The measured time to failure of each product is an observation in SX. So the what you call, there might be a manufacturing industry wherein the number of products are manufactured, right, and that becomes elements of S. But the what is the mean time of failure when a number of devices are so when a number of devices fail, possibility is always there, a particular device might fail. How many devices fail also can be considered, or what is the mean time between failures for each of the product can also be an observation. Similarly, you can have transistors of a particular group or type as elements in S, and the measured maximum switching speed at which each transistor can operate is an observation in SX. Fourth is programs that may be held temporarily in a computer queue. So operating system, generally what happens is when a lot of programs are requesting for the processor or for the memory or whatever it is, so they'll be in a queue. Okay, all those will be part of the S. Counting the number of programs in the queue at a given time gives observation in SX. Okay, so here just we'll write all the programs, but here which programs are in the queue will be corresponding to SX. So these are just examples of the applications of random variables. Then we come to what is known as a very important term, which is cumulative distribution function, which is known as CDF. And CDF for a random variable is defined as fxx is equal to p a colon xa less than or equal to x. Now generally we drop this a, so this a also gets dropped. Then by convention we can write this also. Okay, so even though it is there at 2.8, I thought that because both are related, it's better to specify it at this place. So this is the probability of a random variable occurring for less than x. So for example, might be if you have the dice 1 to 5 as the values of x, 1 to 6 as the values of x. So what is the cumulative distribution function corresponding to fx of 3 will be here xa less than or equal to 3. You can try to mention. So it is conventional to write this value. In general, we could have several different cumulative distribution functions like this. So remember that this and this are capital letters, but inside what we have, which is the so to say argument, u, v, z, within the brackets are arguments, and they are the independent variables. This u, v, z are random variables. This u, v, z are independent variables. So if the independent variable x is equal to small x is equal to infinity, small x is what we are talking here, then that gives us the value 2.2 will give us that this is equal to 1. Okay, this is equal to 1. So fxx is the probability that the observation xa has, or fx infinity is the probability that the observation xa are less than or equal to infinity, which of course is a certainty, definite. So one value is a certainty. Might be should have made it bold because to make it clear that it is a certainty. So if the independent variable is x equal to minus infinity, then it gives fx of minus infinity is equal to probability that xa is less than or equal to minus infinity. That is the value which will give us the value 0. Okay, that is the null value. So that is known as a probability 0 means, say, probability of occurrence of 6 in a grouped dice is 0. If you say it can never occur, so it's an impossible event. It's an impossible event. So for all other values of the independent variable x, generally the cumulative distribution function will be somewhere between 0 and 1. Okay, 1 for everything together. Okay, and if not possible at all, then it is 0. However, it can be anywhere between 0 and 1. Say if you have a dice, and all are equally likely, all the values 1 to 6 are equally likely. In a dice, you can have 1, 2, 3, 4, 5, 6 possibilities. Either you can, when you throw a dice, 1 might appear, 2 might appear, 3 might appear, 4 might appear, 5 might appear, and 6 might appear. So if you say that all are equally likely, then the probability of each one of that occurring will be 1 by 6. P of 1 is equal to P of 2 is equal to P of 3 is equal to, etc. P of 6 equal to 1 by 6, because we have 6 possibilities. So if you want to write f of x3, then it will be 1 by 6 plus 1 by 6 plus 1 by 6. That will be equal to 3. That will be equal to half. Okay, 1 by 6 plus 1 by 6 plus 1 by 6. That will be equal to half. Similarly, if you want to write fx equal to fx of 4 for that matter, capital Fx of 4, then that will be, 4 1 by 6s. That means 4 by 6. That will turn out to be 4. 4 by 6. That is 0.6. 666 or whatever, 667. Okay. Similarly, you can try to find out all that. And if all of them are there, then 1 by 6 into 6 will give me 1. None possible, that will give me the value 0. So we can also see that if a pair of independent variables x1 and x2 are chosen, okay, such that x1 is less than x2, x1 is less than x2, then the then the value of x1 is less than x2 or x2 is greater than x1, either way. So then at that time, you can write that as, f of x2 minus f of x1 is equal to, p of, you can drop this a and a, you can just write p of x less than x2 minus p of x less than x1, and that will be greater than 0. So you can just try to write for this, and you can calculate. So what is the cumulative? That is, the cumulative distribution function defined by 2.2 must be monotonically decreasing. Generally, we say monotone or monotonically non-decreasing. It should always be increasing. There is no possibility of decreasing. Saying this is another way, the derivative, if it exists, okay, if the derivative exists, then it is a non-negative value. Okay, if of a cumulative distribution function must always be a non-negative value. Okay. So
power on. Connected.
So, so to say, we have examples of here. So again, here I have written the same thing. It is conventional to write fxx is equal to p of x less than x, which is there in 2.8. These are just selected examples of the cumulative distribution function. We generally divide them into 3 different types. Continuous, wherein there will be continuity over here. It can take any value of you can take any value, whereas we can take only discrete values here, here, and here, fixed values, and similarly the FUU also can take fixed values there over there, right? So and then this is a mixed type of both some discrete and some continuous. That means In between these values cannot occur. Here, in between these values cannot occur, these values cannot occur, these values cannot occur. Whereas here it's continuous all throughout. Okay. So continuous, discrete, and mixed type. Then we come to the probability models. So generally, before going to the probability models, one of the very important term which we use here is the probability density function, which is known as PDF, which plays a major role. And the PDF is denoted by the fxx, fxx for a random variable x, and is defined as fxx is equal to d by dx of fxx. So it is just a derivative, okay, derivative when if it exists, right? It's a derivative of the so to say, the PDF is a derivative of the CDF, and CDF is the integration of the PDF, okay? And the condition is when the derivative of the CDF exists. So generally, when we talk about that, we can write the inverse also, fxx is equal to minus infinity to infinity fxu du. That is the, what you call, integrated. So on the whole, you can just say PDF and CDF are inverses of each other. This is a very important statement. The PDF and CDF are inverses of each other. So in general, we could have several different probability density functions. Again, same things. Now this U, this V, and this Z should have been capitals. The argument which is there inside the bracket, argument means whatever is there inside the bracket, is an independent variable, small letters U, V till Z. Okay. So now let us come to what is known as the continuous random variables. So we have considered, here continuous, discrete, and mixed. So let us see how the continuous random variables, what all probability models we can have. So here we assume that the CDF is a continuous function, and that except at a finite number of points, the derivative of fxx in the 2.9 exists. So some general features of PDF and CDF are combining 2.7 and 2.9. We see that the PDF can never be negative. The PDF should never be negative. It should be only positive. For any value of its independent variable. So PDF cannot be negative at all. That is small fxx is always greater than 0. So when x equal to minus infinity, 2.1 gives CDF a value of 0, 0. For this value, CDF will be a value 0, a result that we have seen before in 2.4. Okay. That we already considered in 2.4. Here. Yeah. So then, when x is equal to plus infinity, 2.10 with 2.3 allows us to write that very important relation, that is minus infinity to infinity, that is totality. Fxx dx is equal to 1, and this gives us, whenever we talk about integration for a curve which is represented by fxx, this is the PDF curve. So this is area under the PDF curve is always 1. Area under the PDF curve is always 1. So three different things. A PDF can never be negative, right? When x equal to minus infinity, CDF value is 0, and area under the PDF curve is always equal to 1. So these are general features of PDF and CDF, which all the what you call models, the probability models should satisfy, and how they satisfy, we'll see as we progress. So again, using 2.6 and 2.10, we can write P of x1 less than x2 less than x less than or equal to x2 is equal to fxx2. This we already seen, and that is equal to integral x1 to x2 fxx dx. So here this is the probability density function, and this is the cumulative distribution functions for each of the cases. So if the expression for fx, capital Fx is given, you can straight away find this. If expression for small fx is given, then you need to integrate this to find the probability value there. So essentially 2.13 says that area under the curve, PDF curve, or some specific interval in Sx is the probability observations of a random variable occurring in that interval. So from if you want to find this probability, then it just means it is the area under the curve from specific point to specific point, right? So a useful approximation for this is generally, we'll write in place of x1, x2, x and x plus dx, x and x plus dx. Then at that time, this will be fxx, del x. Del x is a small value, x minus the value there. Okay. So finally, we can see that from 2.14 that when del x is equal to 0, the probability that a random variable exactly equals some specific value is 0. That means if I write here x less than or equal to x, then that means x equal to small x, capital X equal to small x. So both the limits are just same, and then at that time, this value turns out to be 0. For any random variable with a continuous CDF, 2.15 gives us some flexibility in the use of equalities and inequalities, and this is true for the continuous case. Okay, might not be true for a discrete case. So for any random variable with a continuous CDF, uses some flexibility in the use of inequalities. So equality and inequality. Equality means equal to, inequality means less than or equal to or greater than equal to. So fxx is equal to p of x less than or equal to x, and this can be divided into two parts, x equal to x and x less than x. So both together will give me less than or equal to. And this is 0. Since this is 0, we can say that only this is what is there. So this becomes equal to this in the continuous case, continuous distribution case. Okay. So let us see some of the examples which occur in the continuous random variables, right? So first we have the uniform distribution random variable, where the observations are equally likely to occur in some interval from say y1 to y2. Okay, constant between y1 to y2. The figure for that can be something like this, right? Equally likely. So the probability density function will be constant throughout. For example, the phase of a sinusoidal carrier in an amplitude modulation system is arbitrary and may be found to be equally likely between plus or minus pi radians. So when you have amplitude modulated signal, the phase of the sinusoidal carrier is generally arbitrary and may be found to be equally likely, which might be somewhere between plus or minus pi radians or 0 to 2 pi radians, whichever you consider. And it will be a constant value. So figure 2.3, which I just showed you there, right, shows you that the PDF and a CDF for random variable y for a uniformly distributed between y1 and y2. The PDF is 1 by this, y2 is greater and y1 is smaller, therefore we write 1 by y2 minus y1. y1 less than or equal to x less than or equal to y2, and 0 otherwise. In the other ranges, it is not there at all.
Power off.
In the other ranges, it is not there at all.
Power on. Connected.
So, and the CDF for a uniform random variable using the 2.10 is the value which is this, fyy is equal to 0 less than infinity less than y less than or equal to y1. From minus infinity to y1 is 0. From y1 to y2 it is y minus y1 divided by y2 minus y1, and between y2 to infinity it will be the totality value which is equal to 1. So if we see here, all the requirements for the continuous CDF and PDF are met over here. That is, PDF is always non-negative and the area under the curve is 1. the CDF is continuous and non-decreasing from 0 to on the left to 1 on the right. So the CDF will have 0, like this will be the curve here, 0 here till this point. Then slowly it is increasing, it is not decreasing at all, and then it will remain constant. So it is never like this. CDF can never be the what you call the value of CDF over here can never be like this. It should always be like this. Okay. So then the third is the what you call the derivative of the CDF exists everywhere except at y equal to y1 and y equal to y2. So PDF is non-negative and area under the curve is 1. CDF is continuous and non-decreasing for between from 0 to the left and 1 to the right, and then the what you call derivative of the CDF exists everywhere except at y equal to y1 and y equal to y2. Because these are the discontinuities. Generally, at discontinuities, we say that the derivative does not exist. Okay. So these are the curves there. Like I have shown you the PDF, which is this value, and this is the CDF, which is just the integration of this from minus infinity to might be y or x, fy y dy. Okay, so you can try to, using that only, this is calculated. That's why it is increasing continuously till this point. Then the example 2.2 is the exponential random variable occurs in discussions of failure rate and reliability and in some queuing applications. We have this figure 2.4. This is your exponential random variables PDF, and fxx is the what you call this one. So this is again monotonically increasing. So this is generally, whenever we talk about manufacturing industry, mean rate of failure, which comes in reliability, and also in computer networks or queuing applications. Queuing applications might be anything, might be you're standing in a queue to buy a railway ticket, or to catch a train, or to go in a bus, or to see a movie, whatever it is, right? So under that conditions also it is the exponential distribution which works out. So fxx is decreasing here continuously exponentially, and capital fxx, so which is the CDF, will be continuously increasing. So if you integrate this, you are going to get this. If you differentiate this, you are going to get this. So expressions can be written like this: fxx is equal to lambda e to the power of minus lambda x for x greater than or equal to 0, and 0 for x less than 0. And the exponential CDF using 2.10 is, 2.10 means integration of this dx from minus infinity to the x value will give us this value. fxx is equal to 1 minus e to the power of minus lambda x 0, x greater than 0, x less than 0, where lambda is what you call the rate constant. I think it should have been greater than 0. I might have made a mistake here. Okay, lambda should be greater than 0. It's the rate constant. Again, all requirements for CDF and PDF are met here. The PDF is always non-negative and the area under the curve is 1. The CDF is continuous and non-decreasing from 0 to the left to 1 on the right. The derivative of the CDF exists everywhere except at x equal to 0. So what you call singularity, sometimes we call it a singularity, or discontinuity occurs only at x equal to 0 here, whereas here the discontinuity occurs at 2 points y1 and y2. So that's the difference there. Okay, so I think we'll stop this for this session. We'll take up the problems in the next session immediately. You just again once more log in once the time is out, right? And then we'll take up the other distribution what you call, which is Gaussian, which is a very important distribution in the next class. I think tomorrow you have a test for maths, I think. So therefore, we will not have class tomorrow. Day after tomorrow, we'll have the class.